It's a very exciting time for AI and machine learning. We all know that. And it's particularly exciting because of recent breakthroughs that have happened, for example, in AI and games like Atari, Go, and for me, maybe the most exciting and interesting one is in poker, where we have computers beating human experts at a game that is quite psychological, that involves deception, and that has incomplete information, which is unlike, for example, Go. It's also exciting because of applications of AI and machine learning to other things that are much more useful, like, for example, speech and language technologies, automatic speech recognition, translation, question answering, computer vision, object, face, and handwriting detection, image captioning. I think a lot of the sciences have been influenced by machine learning and statistical modeling methods. All the recommender systems that we use that recommend us items. Self-driving cars, I maybe say a few words about that. Finance and automated trading. And these are just 6 areas that I could fit on one slide. We could include many, many more. A lot of the excitement in the last few years has come from deep learning, and like Gita, I'll actually mention, I think, some of the same thoughts that came across very clearly in her talk. So there is a lot of excitement about deep learning, and deep learning is one of the things that is driving some of these application areas. But I want to step back and talk a little bit about deep learning, but also let us focus on the limitations and going beyond deep learning as well. So, what is deep learning? I mean, deep learning is basically a reinvention or rebranding of the old idea of neural networks. The idea of neural networks was what got me personally excited about this field in the mid-1980s, when they were popular back then. They just didn't do very useful things, but they were very popular. And what are neural networks? Well, from a kind of mathematical point of view, they're just tunable nonlinear functions with many parameters. Okay, that's all they are. So the parameters in the neural network, let's call them theta, are called weights in the neural network. And neural networks are interesting because, well, maybe they're interesting because they're both nonlinear in the parameters and in the inputs. So imagine you're mapping from some inputs, x, to some outputs, y. They represent a nonlinear function, and it's a nonlinear function of both the inputs and the parameters. So here's one of the world's simplest neural network. It's basically made out of one neuron. This is taking a linear combination of the inputs and passing them through a sigmoid or logistic function, and this neural network is called logistic regression, which has been around for probably nearly a century. Now, what people do nowadays, as well as, again, Gita mentioned this, is to look at deeper neural networks where the function from x to y is represented as a composition of functions. Here is sort of a 2-layer neural network, for example, that represents some sort of nonlinearity, basically. Now, once you have a neural network, what do you do with it? Generally, you optimize something, and the thing that you optimize, whether people admit it or not, is often a log likelihood or a penalized log likelihood. Sometimes it's not, but almost always it maps onto a log likelihood. And the way they're optimized is with stochastic gradient descent optimization, which is just a bit of very standard optimization. So to me, a neural network is just nonlinear functions plus some basic statistics plus some basic optimization. Now, so why is there so much excitement? Well, in deep learning, what people have done is just apply neural networks to wildly more ambitious things than they used to be applied to. And the neural networks that they're using are similar to the ones that got me excited, for example, in the mid-1980s and early 1990s, but with a few differences. So one of them is people had some ideas. Okay, so 35, 40 years have passed, so there are some new ideas in the field. And they've figured out better ways of getting neural networks to train if you have many, many layers. For example, if you stay close to the identity function in every layer, then you can have 100 layers. Because when you compose 100 times something that's nearly the identity function, then you can say, I have 100 layers, but actually you're just making the nonlinearity go not so drastically from the inputs to the outputs. Importantly, also, we have vastly larger data sets. We have the web that allows us to collect huge data sets for computer vision, for example. To go with that, we have vastly larger compute resources, things like GPUs, graphics processing units in the cloud, heavily used now. We have much better software, tools that makes it very easy for people to develop neural networks. And because of all this, we've had vastly increased industry investment, a lot of media hype. And what's meant by all that is that the number of people in the field has increased by at least an order of magnitude, which means progress accelerates because there are more people trying out random things, basically. So the whole field is accelerating, and it's very exciting. But these things have limitations. So what are these limitations? They give amazing performance on many benchmark tasks, but generally they're very data hungry. So we're looking at often problems where you would need millions of examples to solve particular things, and you have neural networks with hundreds of millions of parameters. So from a statistical point of view, it's unsurprising that you might need millions of examples. It's surprising you can do it in only millions of examples. There's some theory that needs to be done there. And I'm sure some of the work on generalization, again, that Gita talked about, tries to address how come they can actually even learn anything or generalize. They're very compute intensive to train and deploy. So it's not very practical when you work in industry. Sometimes you realize you could do it with a neural network, but that's just going to be too expensive. So you might as well do it with a simpler model. This is a particular thing that I'm very obsessed by. They're very poor at representing uncertainty. So when you look at the calibration of the uncertainty that they have, this is not good, and I'll talk about this in a little bit. It's very difficult to incorporate prior knowledge and symbolic representations. So prior knowledge is something that, for example, in Bayesian statistics is quite straightforward to implement, but with neural networks, you have to map your prior onto an architecture and a choice of parameters, etc. That's not trivial. And symbolic representations is what artificial intelligence used to be like in the 60s, 70s, and 80s, where people relied on a lot of logic and knowledge representation methods and so on. And these two areas have yet to come together nicely. Neural networks are easily fooled by adversarial examples. This is a fun thing. I don't know if I have a picture of that. I might. If I do, I'll describe that. But that just means you can take a neural network that confidently predicts something, perturb the input a little bit, and it confidently predicts something ridiculous. And that's not good, basically. They're finicky to optimize. So again, because they're nonlinear in the parameters, it's a non-convex optimization problem. And you have many parametric choices of like architecture, learning procedure, initialization, etc. And generally, they're uninterpretable black boxes, lacking in transparency and difficult to trust. So when you try to solve some real problems, some important problems, not just like labeling images, maybe for your photo collection, but something much more critical, people will say, well, I don't want to use that because I don't understand it. Okay, so I'd like to suggest at least one way of going beyond deep learning. And this is, personally, my view on an interesting direction to take this field. And that is, again, I think, Gita mentioned this during her talk. Let's think about modeling. And, we have, I think, this distinction between data-driven models and mechanistic models. But what's the model in the first place? What do we mean by model? And here I'm going to describe what I think a model is, as simply as I can imagine it. So a model should be description of data that one could observe from a system. Okay? So the way we evaluate if a model is good is to see, well, what kind of data would the model predict? And then does that match the real data or not, basically? That's the whole concept of falsifying models, basically. Of course, models might be also simple and understandable or so on, but it's hard to quantify those. Whereas if you say, well, how well did it predict the data that you actually observed, then you can actually say whether a model is good or not. And because the process of making statements about data, well, you have the data that you have observed, but if you want to make statements about any other data, then any sensible model should be uncertain about the statements it makes about other data. Like, you wouldn't trust a weather person if they confidently told you exactly what the weather was going to be like for the next month. Their predictions come with uncertainties. And so we're going to use the mathematics of probability theory to represent all forms of uncertainty and noise associated with our model. So this is a Bayesian view on probability theory. This used to be the dominant, conception of what probabilities meant up until the beginning of the 20th century. And basically, we're going to use probability theory not to represent repeatable experiments, because most of the time we're making statements about things. It's not about repeatable experiments, but to just represent uncertainty. And I don't even like the terms randomness and noise, because I don't really believe in these things unless we're talking about quantum theory, but I definitely believe in uncertainty. I think uncertainty is just fundamental to modeling. And then we're going to use inverse probability, which is just probability theory, nothing new, really. And that's Bayes' rule and all the associated things that go with Bayes' rule to infer unknown quantities, adapt our models, make predictions, and learn from data. And so I'd like machine learning people to think this way. It makes life easier. And then deep learning can fit in very nicely. Actually, I'll show you how it can fit in. All right, so in this worldview, there are two kinds of things. There is data, which you measure. Anything that you actually measure, that's the stuff in green. Green is good. You've measured it. And there is everything else, hypotheses, models, parameters, anything that you don't measure. Okay? And the framework basically says that we want to infer things about the stuff we didn't measure from the stuff we measured. So that's this posterior probability of the hypotheses given data. And the way you do that, according to Bayes' rule, is before you observe the data, you have to formulate some prior, which represents your state of belief about the stuff that you didn't observe. So if you're doing model-based, inverse modeling, for example, then you would have a prior on what lotus leaf cross-sections look like, for example. That would be a model to me. It's like a prior on, what tumors might look like in a tumor, scan or something like that. That's the prior. And then for any hypothesis, you can score the hypothesis by the probability that it gave the data. You multiply the two, you renormalize over the space of hypotheses you're willing to consider, and that gives you the posterior over hypotheses given data. And learning and prediction can be seen as forms of inference. So again, in the language of sort of statistics and machine learning, we're going to take the very two simple rules of probability theory that I have kind of in my head, from which I derive everything else. And these are the sum rule and the product rule of probability theory. Bayes' rule is just a corollary of these. And then if we take these rules and we substitute for x and y the things we're interested in, like D for data, theta for parameters of a model, m for the class of models, then we can say learning is the process of going from the prior to the posterior via the likelihood. And then this term in the bottom here is called the marginal likelihood or model evidence, which itself is quite interesting. Prediction, if I'm trying to predict some unknown quantity x given the observed data d and my model, then that involves averaging predictions over all parameter values, theta, weighted by the posterior probability of those parameters, which we computed up here. And then if I want to compare different model classes, then I would apply Bayes' rule at the level of different model classes here. So you don't have to invent new things, you just kind of follow the rules. It's quite boring, but it's simple. Okay. All right, so so why do probabilities matter for artificial intelligence? A lot of the people, for example, currently, if you talk to most, students in machine learning and AI at a big conference, they don't really think this way, unless they're my students or, my students' students or my friends' students, so on. Okay. They don't generally think this way. They just think, I'm going to build a big deep neural net, I'm going to throw lots of data at it, and if I'm lucky, I'll get a state-of-the-art result, I'll publish a paper, I'll get 1,000 citations. Okay, that's kind of what they think. Well, why do probabilities matter in this day and age? Maybe you can do all that without knowing any probability theory. You just need to know TensorFlow and write some code or whatever. Well, here's why I think it matters. So calibrated models and prediction uncertainty are important. You really want systems that know when they don't know. Okay? And in particular, for example, I don't want to spend too much time talking about this, but if you're trying to build a self-driving car, you'd really like it to know when it doesn't know something. Okay, that's quite important. You can use this framework, this probabilistic framework, to deal with a lot of the difficult problems that seem kind of hard to solve. Like, for example, automatically doing complexity control or structure learning. You can use the concept of Bayesian-Occam's razor, which just follows from probability theory, to choose between different architectures of a neural network. I mean, nobody's really done that. I mean, I've tried doing that. It's computationally hard, but it's conceptually incredibly straightforward. Okay. You can build, I just pressed the wrong button. You can build systems that make rational decisions. I mean, if you want to build a system, you'd like it to be more rational than the typical human. You don't want to just mimic what humans do. You want to say, well, what does rational behavior mean? What is the theory of rationality? And a lot of people would argue that the theory of rationality means having coherent beliefs about a set of propositions and then making decisions that minimize some sort of loss according to those beliefs. And this Bayesian framework is actually a very nice framework for thinking about rational decision-making. Probabilities are good. This approach is good for building prior knowledge into learning systems and making sure that that knowledge is updated in a coherent and robust way as you get more data. And then we want to make sure our learning algorithms work on both small and large data sets. We're kind of, we're in the era of big data, right? And we can get excited about what we can do with big data. But there are a lot of problems where you have small amounts of data, and you're never going to have big data. And those are really, really important problems, including some problems which might seem like big data, but they're not really big data. For example, for medical problems, you might have, the whole National Health Service worth of data in the UK with, 60 million patients. But for every single patient, you have a small data set. Okay? And for that patient, they don't care about you having big data. They care about the fact that you only have a small amount of data about that particular person. And so many big data problems are actually large collections of small data problems. Okay, so what I want to spend the rest of the time talking about is some current and future directions in probabilistic machine learning and AI. And here's sort of a map of kind of my interests and my group's interests. And a lot of them center around the idea of automating machine learning. And I'm not going to talk about all of these, but I think I'm going to talk about 3 of them. Bayesian deep learning, how to bring Bayesian methods together with deep learning, probabilistic programming, and the automatic statistician. So in Bayesian deep learning, the idea is the following. Okay. So you have a neural network. I already said a neural network is just a nonlinear function. Okay. And, well, it has parameters, and so rather than optimizing those parameters, we can basically do Bayesian inference on those parameters. We have a prior on the parameters of the neural network, and we get some data, D, and we try to estimate the posterior on the parameters of the neural networks. Alpha are hyperparameters that we might do inference on or, you know, estimate them with points. Estimates. And then prediction involves averaging over parameters. Okay, so conceptually this is very simple. There are a couple of issues here. So one of them is neural networks by design are hard to think about. Okay, because you know they have so many parameters. Most normal machine learning researchers and statisticians have a difficult time having kind of informed priors about what should, you know, the weight connecting this neuron to this neuron represent, okay? What should be the prior on this particular weight? How should it relate to the prior on this weight? You know, if you have 100 million weights, how do you elicit priors like this? And the important thing is, if we think about a neural network just as a function that maps from inputs to outputs, our prior on the weights, our prior on the parameters here, is actually an indirect way of specifying a prior on functions, the map from x to y. So really what we should do is we should have some intuitions about what the functions are that we want to capture, and then figure out how to come up with priors on the weights that represent those functions. And one very helpful piece of theory, which is now, you know, 24 years old at least, is the fact that a neural network with one hidden layer and infinitely many hidden units, and a Gaussian prior on the weights, it's a little bit more general than that, but a neural network with a single hidden layer, and when you take the limit as the number of hidden units goes to infinity, that converges to a Gaussian process, which has been studied in statistics for about 100 years. And so that gives us an idea about what the prior on functions might be for neural networks. So that's an old result. Gaussian processes are beautiful in their own right, something that many of us have worked on. And this link is very deep between neural networks, Gaussian processes, and support vector machines, which are basically non-Bayesian versions of Gaussian processes. And we've just recently extended this result to, this is a paper that just appeared this year in iClear, it's sort of a main deep learning conference, to show that Gaussian processes, this Gaussian process behavior also occurs in wide and deep neural networks. So if I make my neural network deep, then if the layers are wide, it still ends up just being a Gaussian process. If the layers are narrow, then it might not be a Gaussian process. Okay, and it depends, this obviously depends on the prior I choose on the weights, but for many of the choices that people have studied in the Bayesian machine learning literature, they've been working really hard at analyzing something that is just Gaussian processes. So it's kind of a little bit of a negative result, but it's also very interesting. So the idea of combining Bayesian methods with neural networks is actually quite an old idea. And one thing I want to really distinguish is between conceptually two different things, and it's important not to confuse them. The two things are models and methods, okay? A neural network, to me, is a model. It's a representation of a class of functions or something like that. Gradient descent, or stochastic gradient descent, or Bayesian inference, or convex optimization, those are methods, okay? Methods for dealing with the parameters of a model. So we can mix and match. I can write down, I don't know, hidden Markov model and optimize it using maximum likelihood gradient descent methods, or I can do it with Bayesian methods, or maybe I can convexify sometimes and do convex optimization on some parameters, etc. So let's distinguish between models and methods. And neural networks as a model have been combined with Bayesian methods for a long time. And I think some of the seminal work in this area goes back to the work of David Mackay in his thesis, where he used Laplace approximations on Bayesian neural networks. The work of Radford Neal, which I also alluded to, where he applied Markov chain Monte Carlo methods. Hinton and Van Camp applied variational approximations. This was rediscovered by the recent deep learning community. And people have applied a number of different methods to approximate the posterior over the parameters of a neural network. And why would they do that? Well, one of the reasons to do that relates to quantifying uncertainty. When you have data, you want imagine you're mapping from X to Y. Where you have data, you want to be fairly certain about the function, but where you don't have data, you want to be uncertain. Okay? And so when you get point estimates of the neural net parameters, the uncertainties tend to be highly underestimated outside of the data region. So we've organized a couple of kind of fairly big workshops at the NIPS conference on Bayesian deep learning. If you're interested, you can look at the webpage of those. This is a figure from my student Yaron Gal's thesis, which is on this whole topic. I want to mention one particular idea, which it's just some recent work that we did, where we combine deep learning with Gaussian processes. So Gaussian processes are these very flexible prior over functions. And essentially what we do is we take a deep learning architecture and we put a Gaussian process at the end of it. Why do we do that? Well, the reason we do that is because we want to have the best of both worlds. We want to have all the sort of flexibility of a deep learning architecture, and then we want to have reasonable uncertainties coming out from the Gaussian process. So this is one heuristic way of doing that. Now, algorithmically, it's made easier because we wrote a library called GPFlow. So if you know something about the deep learning community, they like their TensorFlow libraries for optimizing things. And GPFlow just makes it possible to do Gaussian processes within TensorFlow. So the whole thing becomes, from the software point of view, just like one big neural network. And I want to just show you some pictures. The point is we want systems that know when they don't know. So I'll skip over this a little bit. This is the picture I want to show you. Imagine you have a data set. You're trying to do classification, 2D classification. You have two classes, the orange class and the blue class. Okay? So this is an easy classification problem. Now, if you apply standard neural network, let's start here, it classifies this very well. But if you look at how it extrapolates, well, what's going on? It's very confidently saying orange class out here, and very confidently saying blue class out here. So outside of where it's seen data, it's making extremely confident predictions, where I don't think it has any, right to make those predictions. If you take a Gaussian process, this is a very simple two-dimensional problem, so we can apply a very standard Gaussian process. It does something much more sensible, which is it classifies the data correctly, but away from the data, it says, I don't know, 50%. Okay? That's what the white region means. And so if we do these Gaussian process deep neural nets, we get kind of like the behavior of this. We get a little bit of spillover from the fact that you have a neural network in there, but that's kind of what we want. We want the power of a neural network, but we want it to basically get uncertain away from the data. So I think this has a lot of promise, and this gets better at dealing with adversarial examples, but I'll skip over that. Here's another thing that's interesting. What happens if you train a neural network on some data set like MNIST, and then you test it on other data sets, okay? So you don't retrain it, you just test it on other data sets. This is something we're calling transfer testing. Now, a good system would at some point start saying, I don't know. And actually, neural networks don't do that. They tend to very confidently make predictions, whatever you give them. Okay, so that's pretty bad. And here, I'm not going to go into this, but we have our Gaussian process deep neural network is better. It's not wonderful, but it's certainly better at not being overconfident. So the second, I was going to talk about three things, and I know I don't have much time. The second thing I wanted to talk about is an area called probabilistic programming. And this area is, I think, really, really exciting. So the problem is, if we want to do probabilistic modeling, we have to write down a model of a system, and then we have to write some code for doing inference in that. And this is time-consuming and error-prone. It could take, you can make many errors. It could take months to do this. But we'd like this to be as easy as using a compiler, okay? One of the revolutions in computer science was when somebody figured out you don't have to write machine-level code. You can write high-level abstract computer programs and then get the computer to translate that into machine-level code. That's the idea of a compiler. So we're going to have something like a compiler for probabilistic models. So this is the idea of probabilistic programming languages. You express your probabilistic model as a computer program that generates data. In other words, like a simulator. You can put mechanistic parts in there. You can put, differential equations in there, whatever you want. It's just a computer program. In fact, any program that you write down that calls random numbers is a probabilistic model, okay? And then the magic is the following, which is you can have a universal inference engine for these programs, which is essentially doing Bayes' rule on computer programs. So we're used to running computer programs in the forward direction, which would generate outputs given the inputs. But what about you have a computer program, you say, these are the real inputs that I've observed. This is my climate model. This is the real climate that I've observed. What should the parameters of my climate model have been, and with what distributions, to match this real data? That's the basic idea. And there are a lot of examples of this. There is a long history. In fact, systems like bugs are an early and very important form of probabilistic programming language. Stan, Church, a lot of these. And I've worked on, with my team, on two different recent probabilistic programming languages. And under the hood, what's happening is you have MCMC methods, particle filtering methods, variational methods, etc., implementing things. Okay. So here is a hidden Markov model written in Turing, which is our probabilistic programming language based on Julia. It's very simple. You just write that, and then you say, here's the data, and it just goes and does inference. Here's some links to probabilistic programming resources. And in fact, at Uber, we actually put together a probabilistic programming language that combines deep learning architectures. It combines something called PyTorch with universal probabilistic programming. So we actually use this in the company. So I don't have much time for the rest. I'm just going to give you a little flavor. The third thing I was going to talk about was AI for data science in the form of the automatic statistician, which is a system where you give it data, it searches over models, and it produces a report, fully automated. And the report tells you patterns in the data. And so here's like the first page of these computer-generated reports. These are 10 to 15-page reports. And this is a service we're going to put online very soon. And then the last thing I wanted to say was just, we do a lot of AI at Uber, and we use probabilistic modeling for it. So I'm going to skip over most of this. This is a quote from our CEO. Uber is a giant machine intelligence problem because we're basically building models that navigate in the real world and that has a lot of uncertainty. I'll skip over this. So what are the AI problems that we have? We have problems in space-time with forecasting. We do long-term forecasts, short-term forecasts, real-time forecasts at many levels of space. This is predicting driver and rider demand and supply and then trying to match it. These models go into pricing algorithms that try to optimize the market, including information about day of the week, holidays, weather, type of vehicle, etc. We try to predict ETAs, expected time of arrival. We have dispatch algorithms. We have a food delivery system where we try to pick, we model like how long it takes to prepare a meal, because then we can send the courier to pick up the meal just as it's finishing, etc. Of course, we work a lot on self-driving cars. For perception, prediction, motion planning, we use AI methods. We even have flying cars planned by 2023, so that should be fun. Madrid traffic is pretty bad, so I'm sure many of you would like to commute in one of these electric flying cars as a passenger service. The idea is for it to be affordable, clean, and efficient. Okay, and lots of other things. So I'm going to skip over all this. To conclude, so probabilistic modeling offers a framework for building AI systems that reason about uncertainty and learn from data. And then combined with decision theory is the foundation, I think, of our rational decision making. I've briefly reviewed 3 areas that we work on. And this is a review paper from 3 years ago now that talks about probabilistic machine learning and AI. Okay, so thank you. Okay.